Graphical methods. Now we have learned the graphs of quadratic functions of the form y is equal to ax squared plus bx plus c, and how to use these graphs in solving quadratic equations by drawing suitable straight lines. Now we look at the graphs of cubic function. The cubic function takes the form y is equal to ax cubed plus bx squared plus cx plus d. Most of such graphs have two turning points, unlike those of quadratic functions, which had one turning point. Just like in quadratic graphs, we first find the values of y for the corresponding values of x. For example, let us plot the graph of y is equal to x cubed minus 3x squared minus 9x plus 2 for the range of x between -3 and 5. So we first come up with a table of values. The table of values will appear as on your screen. Now we plot the values on a Cartesian plane, and we shall have the following graph. Solving cubic equations. Now, just like their quadratic counterparts, cubic graphs can be used to solve cubic equations. How? For example, plot the graph of y is equal to x cubed plus 2x squared minus 5x minus 8 for the range of x between -4 and 3. Use the graph to solve the following. X cubed plus 2x squared minus 5x minus 8 is equal to 0, and minus x cubed minus 2x squared plus 3x plus 3 is equal to 0. Now, as usual, we make a table of values for the range of x between -4 and 3 and find the corresponding values of y for that equation. So we have the following table of values. If we plot the values on a Cartesian plane and join the points, we shall have the following graph. Now, to solve the equations, we subtract them from the equation of the curve. That is, y is equal to x cubed plus 2x squared minus 5x minus 8. The whole subtract 0 is equal to x cubed plus 2x squared minus 5x minus 8. And if we subtract, we get y is equal to 0. So we find the values on the graph for y is equal to 0. And the line y is equal to 0 is the x-axis. Our curve cuts the x-axis at 3 points. That is, x is equal to -2.8, x is equal to -1.3, and x is equal to 2.1. These are the solutions of the equation x cubed plus 2x squared minus 5x minus 8 is equal to 0. For the second one, we do the same with b, only that this time we shall add the two equations. Basically, in solving the equations, the idea is to eliminate the functions of x cubed and x squared, and this can be achieved by either adding or subtracting the two equations, which allows us to have a linear line. So we have y is equal to x cubed plus 2x squared minus 5x minus 8. The whole plus 0 is equal to minus x cubed minus 2x squared plus 3x plus 3. If we add, we have y is equal to minus 2x minus 5, and that is an equation of a straight line. We plot the graph of y is equal to minus 2x minus 5 on the same curve, and we shall have the following. Now the line cuts the first curve at the point x is equal to minus 2.7, x is equal to minus 0.8, and x is equal to 1.5. And these are the solutions of the equation minus x squared minus 2x squared plus 3x plus 3 is equal to 0. Rate of change. Since dependent variables are plotted on the y-axis, the rate of change is a measure of the gradient of a curve. That is, the rate of change is equal to gradient, which is equal to change in y-coordinate over the change in x-coordinate. The gradient of a straight line is constant, but that of a curve changes continuously. As such, the gradient can only be determined for specific points. This is done by drawing a tangent at that point and finding the gradient of that tangent. For example, consider the curve on your screen. On this curve, AB is the tangent to the curve at point P. The rate of change at P is given by the gradient of the line AB. That is 3 minus 0 over 3 minus 1, which gives us 3 over 2. Average and instantaneous rate of change. Consider the curve on your screen. Now, the gradient of PQ is the average rate of change between point P and Q on the curve. On the other hand, AB is a tangent to the curve at D. Its gradient is a measure of the rate of change at point D. This is called the instantaneous rate of change, meaning the rate of change is at an instant. Equation of a circle. Now consider the figure on your screen, which is a circle drawn on a Cartesian plane. The circle has radius r and center at A with coordinates a, b. P with coordinates x, y is a point on the circumference of the circle. AB and PB are perpendicular at B. From triangle APB, AP is equal to r, AB is equal to x minus a, and PB is equal to y minus b. Now, using the Pythagoras theorem for right angled triangles, x minus a squared plus y minus b squared is equal to r squared. That is, base squared plus height squared is equal to hypotenuse squared. This is the equation of any circle on the Cartesian plane. For example, find the equation of a circle with center at 2, 3 and a radius of 5 units. Using the equation, x minus 2 squared plus y minus 3 squared should give us 5 squared. Now we expand the equation and we shall have x squared minus 4x plus 4 plus y squared minus 6y plus 9 is 25, and finally we have our equation as x squared minus 4x plus y squared minus 6y minus 12 is equal to 0 is the equation of that circle with a center at 2, 3, and a radius of 5 units. In another example, find the center and radius of a circle with the following equation: x squared plus y squared minus 2x plus 4y minus 11 is equal to 0. Now in the solution, we first pair up the like terms. That is, we have x squared minus 2x plus y squared plus 4y. We equate it to 11. For each pair, we complete the square if you remember your quadratic equations. That is, we make it a perfect square. So we shall have x minus 1 squared plus y plus 2 squared is equal to 11 plus 1 plus 4. And we shall have x minus 1 squared plus y plus 2 squared is equal to 4 squared. Relating this to the equation of a circle, you'll find that the center is at 1 minus 2 and the radius is 4 units.
One of the wonderful things about mathematics, I think, is that people are impressed. It's often seen as a very hard subject, and so if you've done math, it's often treated as an entrance requirement, as a credential to do lots of other things. And so one idea is that for example, some MBA programs, the only thing they require going into it is a good, solid math understanding. They can teach you all the business. They just can't teach you the math fast enough. And so I think that math, aside from obvious careers that require math, if you're going to go work in a department that does operations research or something like that, they'll want people with specific skills in mathematics. But math is often seen as a filter or as a screen for many, many other disciplines. And so I guess what I'm trying to say is you can think broad because math actually is a solid preparation. It's a good credential to go into lots of different fields that people often don't consider at the beginning.